Discrete time systems can be analyzed by looking at the characteristic equation poles and zeros of the transfer function h of z. As a first step, we will derive the transfer function h of z from the equation y of k is equal to h of k convolved with x of k, where h of k is the impulse response of the system, x is the input signal, and y is the output signal. Applying the z transform yields that y of z is equal to h of z times x of z, where the transfer function h of z is equal to the z transform of the impulse response h of k equal to y of z divided by x of z. To derive the transfer function of a causal system for which the input-output equation may be of this form here is given, apply the z transform and solve the equation for h of z, which is equal to y of z divided by x of z, so that the transfer function h of z is equal to a polynomial of z with coefficients b divided by a polynomial in z with coefficients a. The numerator of the transfer function is denoted n of z, and the denominator is denoted d of z and is often called the characteristic polynomial of the system. Setting the characteristic polynomial d of z equal to 0 yields the characteristic equation of the system. The values of z which satisfy the characteristic equation, which means the values of z for which ds is equal to 0, are called the poles of the system. And since the system has coefficients a0 to an, which means that the denominator is a polynomial of order n, the system has n poles. Finding all values of z for which the numerator n of z is equal to 0 yields the zeros of the system. The transfer function h of z tends to infinity at poles and is equal to 0 for zeros.